Hi, everyone. I'm Manisha, the founder of Modulo, and I have a very special treat for you today. This is my Science Guys podcast, and I am welcoming three incredible humans who I have known for a couple years now, all teachers who developed their own funky science programs, which we recommend on Modulo and love. We have Brandon Hendrickson, Dan Freed, and Michael Finnegan. And they are respectively Science is Weird from Brandon, Biochemistry for Kids from Dan, and Quantum Courses, right? Is that what you're going by now? And maybe I'll just start with my own take on your programs and why I'm excited by them. So Brandon in Science is Weird is just kind of completely breaking apart everything we think and know about learning science and education in this really wild and wonderful way. And he's built a whole community around this totally mind-blowing approach. And Dan Freed has been taking this, deciding to teach biochemistry to little kids because he can, and his method is very influenced by some teachers who have come before him who said, let's tackle really advanced topics with young kids, and he has a really unique way of doing that. We have a couple Modulo kids in common who just love his classes. And Michael was the first teacher entrepreneur I discovered way back when I built my first homeschooling startup in the Bay Area. He started by offering science classes to kids and co-ops, and now he's developed this incredible online program where you could actually do physical labs as a homeschooler, which is so rare and special. And I love each of your approaches to learning. And in the world we live in where there's so much information, helping kids learn to think critically and to learn to think scientifically is as vital as ever. And so I'm just really pleased to have all of you here today. Welcome.
Thanks for having us. Thank you.
Yeah, so maybe let's see, where should we start? Brandon, do you want to talk a little bit about your journey from science teacher to science curriculum builder and what inspired that?
Journey actually makes it sound more intentional than it actually was.
I don't even like that word. I don't know why I used my banned word list.
It's a journey in retrospect, right?
Yes.
It's a bunch of weird wandering, and one day you wake up and you say, I'm a what now? What is it that I teach? I grew up, the one topic, I was interested in everything growing up except for science. I actually avoided science classes insofar as I could in high school. In college, I took rocks for jocks, and I took a course on geography, which is fun, but is not really even qualifies as science in a lot of people's understandings of that. And then after I graduated, I just started working with the homeschooling community and taught absolutely everything except for science, because I knew that this was my great gap in my knowledge. Meanwhile, I was reading all of these really fun books on science. I read probably more science books than I did almost any other kind of book, but I couldn't teach it because I had never taken, an actual chemistry course and an actual physics course. And then I was the curriculum architect for a Montessori-ish startup school outside of Seattle. And I found myself teaching and really loving teaching science when I had the freedom to do this. And then the pandemic hit, and I thought, I think I can actually take these classes and put them online. And everything has kind of rolled from there. So I actually come to science from an outsider's perspective, which I think is insofar as I'm doing something that is unusual, I think it might be the secret sauce that I'm fresh to learning a lot of these things. And so we have a science advisor. We do a lot of research to make sure that everything that we teach is absolutely true. And we develop this very, very high level sort of content. We have a disproportionate number of students whose parents have PhDs in the sciences, who are frequently listening in the background. Sometimes they say that they wish they wouldn't, but they in fact are not able to stop listening in the background, and they report hearing all sorts of really interesting new things that they had never known that just blows their brains before. So I come to this from an outsider who gets to communicate my, holy crap, can you believe that the largest volcano in the world is, sorry, Manisha, do you know what the largest volcano in the world is?
I think it's in the water. It doesn't come up high, and so it's surprising. That's what I remember is that it's one of those trivia questions.
Totally correct. And most people will say that it's the big island of Hawaii for that. But it turns out that by any rational calculus, the largest volcano in the world is the Atlantic Ocean.
Wow. Okay, so
Pen-
Brandon, I
sorry.
have a question for you because
Yeah.
I really want to get at this because your approach is very, very different than other approaches to teaching science. How can you define that for people in terms of how science is usually taught and the approach that you're coming from?
We started with the question, if people were to design the 3rd through 8th grade science curriculum, we have some younger kids, we have a bunch of older kids too, but if they started to design that curriculum now, as opposed to the beginning of the 90s, with everything that we know, with like this sort of like gluing together this consilience of all of the different levels of science, how would we make science? And then we don't do the thing where we say like, here's a year of chemistry, here's a year of physics, here's a year of biology, but we take a very serious course in chemistry, physics, and then chemistry, and then anatomy, and then earth science, microbiology, and zoology. Every single year, we take a weird topic for each. We just finished volcanoes, where now we're on to something, apples. And we then try to knit those things together where every topic becomes sort of a portal into the weirdest, most important aspects of modern science through that topic. And then that knits together with everything else. And then all of our lessons are these like hyper interactive, super engaging riddles that I just pose some sort of simple question, like what's the biggest volcano in the world? And then I don't just tell the kids the answer, like I have the kids figure out the answer by giving them clues in the forms of metaphors and stories and weird images and stuff like that.
Yeah, I love your use of the word riddle. It's almost like you're helping shape and transform their processes for thinking. I want to come back later to this point of how you make sure everything is absolutely true. So think about that one. But maybe, Dan, what gave you the idea that you could be teaching biochemistry to little kids, and where were you in your career when this idea evolved? And
yeah, so a lot of what Brandon said, I totally agree with, the outsider view. So I really got interested in education. My parents are teachers. I really like, I was into learning, but I started off college as a music ed major, and I got into teaching very little kids in Center City, Philadelphia, using this theory called the Gordon Learning Theory. And I was very influenced by this idea of teaching modal music and odd non-Western meters to little kids to try to cultivate their musical aptitude at a very early age. When I switched majors to science, I brought a lot of this music pedagogy with me into science learning. So that's like the outsider view. And I think it's sometimes hard for science people to see like what I'm doing, because I'm influenced by art and music learning like heavily. And I have, this idea that there's really the limits that are put on kids through traditional standard-based learning. Like we said, if we were going to redesign this, not starting from 1900, but right now, like what would we do? So during my PhD, I kind of started to apply this idea as I was learning this amazing like structural biology information and molecular biology. I was like, why can't kids learn this? Like, why did I have to take a PhD from Yale to learn this stuff? Like, you could teach this to 3rd graders. So then I began experimenting. We heavily use these kinds of molecular models to do all kinds of high-level biological, understanding. And same as Brandon, during the pandemic, these ideas kind of crystallized, and we found the homeschool community. And I just really began to, go to bring this to the end of what it could really do. And I've been working with kids all over the world. Like thousands of kids have used the program at this point. Really, what we're doing is I'm using, very cutting edge structural and information and data from experiments that are just a couple of years old. And a lot of the lessons that I'm doing couldn't have been done 5 years ago, because it's about, the most modern understanding of how the heart beats or how the eye senses light, something like that. So we can build this amazing scaffold to get the kids to understanding what I feel like should be commonplace knowledge. Like, how does your heart beat? How do we see? How does a muscle move? But it does require like a lot of technical understanding. So these kids are sometimes in this for the long haul. They're in this with me for years. And the level that the kids are at is just like unprecedented. And I wish we could get some more attention for what is happening in these classes. But for everyone from a kid who just wants to learn a little bit about chemistry to kids who want to go on this journey with me and learn as I learn also. That's kind of what
I'm so curious about this analogy with music because, Jeremy Howard, who's a parent in your program, and Angelo is really passionate about music as well. And he's also a well-known scientist. Could we explore that a little bit more in learning music and learning science and what the link is there?
Yeah, like it's a little bit hard to put your finger on it. But, there's certain things about practice and the idea of like, what does it really mean to internalize something? So whereas a traditional science class, you may, I'm studying for this test and I know how to prepare for these questions and then I get the right answer and then I'm such a great student and I got 100. Whereas in music, that doesn't exist. That music, it's something that is emotional. You do it not to get a score on a test or to win something. You do it because this is something that you have as part of you. And that's maybe the core of what I'm doing. So I do this because this is something that I think is important, and it's like an appreciation of the world, and it's like a connection to the world, the way music or art may be used to connect with things and people. So that's really where it starts with. And then there's a lot of like technical things like how I actually approach like the idea of practicing or studying. It's a little bit more blended with what I always grew up with in music and art, where you're very you're looking at things in different angles, and it's a very different like look to a traditional assessment of a science class. So that's where it comes from.
That's lovely. I mean, I think that I would have enjoyed chemistry a lot more had you been my teacher. I remember being terrified of labs and almost, I think, willfully failing every single time to execute these cookie cutter experiments that were not really experiments, but more like recipes in my chemistry class. And as a more creative, artsy person, I think I would have really loved bringing some of that to science.
Yeah.
Michael. Yes, exactly. Michael, better segue. Michael has probably been in this homeschooling world for the longest, well before the pandemic. Back in the good old days when we were in the Bay Area, so how did you get started with homeschooling? Were you homeschooling your kids? And maybe tell us a little bit how your course has evolved over the years, because it has evolved so much.
That's right. Yeah. And just to sort of piggyback on what Dan said, I mean, it's correct. I mean, learning for kids is such an emotional experience. If you tap into their emotion and engagement and joy, you don't got to do anything after that. So yeah, I'm kind of like the roughly speaking, the photographic negative of Grandin, roughly speaking. So I was in science. I was like an insider. Like in high school, I loved physics, but was not really good at it. And so I got like an A in calculus in my senior year in high school. That's pretty good. A in calculus. But if you ask me anything about what calculus was, I would have no idea. Even after college, I was an engineering major. Somebody said, "What's calculus?" or "What's describe the meaning of quantum physics or Newton's laws or anything in electromagnetism." I didn't know. I can take a test, maybe do okay, but I didn't know. So I started reading all these like history books of science and of how these ideas developed in history. Because at some point in time in history, we knew that the form of water was H2O. Or sometimes, some point we didn't know that. At some point in time, we did know it was H2O. At some point in time, we didn't even know hydrogen and oxygen existed. At some point in time, we did know that hydrogen and oxygen existed. So when I dove into, I almost became like a scholar of science history. When I dove into that, all these, the evolution of how humans learned this stuff just really sank in. And even like in the basic ideas of calculus just made so much more sense. So I'm like in my mid-20s by the time I actually figured out what I was doing okay on back in high school. So actually in my PhD program, I started volunteering with some in Oakland schools, some underserved schools in Oakland. And I'm kind of a miserable PhD student. And I get to go hang out with these kids for a few after school periods. And I'm loving it. I can talk science. I didn't know I could talk science to kids. These kids are responding to me. Like immediately there was almost a career change. Although so I'm not a photographic negative to both Dan and Brandon, the fact that I kind of come from the outside at least when it comes to education. I didn't know this. And then I read about, I got a job at a Montessori school and I read all about Marina Montessori, and I was just like overtaken with the beauty of this lineage that she is a part of in education. And there's theory and practice and thought. So I studied ways of learning and ways of teaching. It's not just like what you get in traditional public schools where you sit in a desk and look at a whiteboard and listen and take a test. And so all this stuff was circulating in my head. So I decided to break out on my own. Where can you break out on your own where you're not like impeded by some regulation or you need a whole bunch of, compliance? And that was a summer camp. You could do whatever you want at summer camp. So I started running these summer camps in the Bay Area, and I wanted to go. So I was like, might as well go big early. So I was like, let's do quantum physics for middle schoolers. Why not? And so basically the pedagogical approach, which is still what we use today, was like, what the heck happened in history for like Niels Bohr, Albert Einstein, especially Niels Bohr in 1913, to be like, hey, here's what the atom looks like. It looks like, a solar system. How did he know? He never saw an atom. How do you know? So I just went back and it was a series of like fairly simple experiments that guess what middle schoolers can do that were done in the 17 and 1800s that led Niels Bohr to make this leap. And if you throw some guiding questions and guiding thoughts in, by Friday of that first camp week, this is like 2010, kids are like, and these are like just average kids, Oakland, Richmond, California, Berkeley. They're like, hey, Michael, does this mean the electron could be here and here, but not here? It makes no sense. I'm like, yeah, it makes no sense. And so that's when I kind of knew this. So I call it a radical first principles approach, where you literally start from before humans knew anything, and you just do the experiments that humans did. And so the kids are literally on the front lines of history, working with Galileo, working with Newton, working with Faraday, working with Joseph Priestley, Lavoisier, everybody. And they got things wrong, and that's the spirit of quantum courses. It's not about getting the right answer. It's about doing labs. That's all the data you have. Make a claim and back it up with the data you have. So yeah, that's kind of like the evolution of basically up to today.
It's amazing, Michael. So I think there's something you all touched upon, which I'm really curious about. I was listening to, on the Jimmy Kimmel show, there's this flat Earth society of people who actually believe that the Earth is flat. And their arguments are that like NASA is developing fake photos and such. And I was kind of curious, if I don't think that your programs really attract the types of families that might join a flat Earth program. But, if you had a student come in with that kind of idea, like the Earth is flat, so something which is pretty much universally accepted in science, how would you approach that? Whoever wants to start.
I'll start only because I have not, to my knowledge, had a flat Earth family come into class. But I've recently discovered that there is a long-running rumor online that I'm a flat earther. And that is because when we started off our sort of revamped big 6-year-long cycle of classes, the very first lesson that we encourage families to start with is about the flat Earth. And in the lesson, I resolutely refuse to say that the Earth is a sphere, that the Earth is a ball. Obviously, the Earth is a ball, but this was our, I guess, in some ways, Manisha, this is getting to the question of how do we help kids understand, like, what is truth really? We start by really problematizing truth and saying and asking, how does, like, science makes these huge claims, right? Like, you should trust us, trust the science. Every group has said that over thousands of years. This is a huge question. What is it that makes science actually different from any other group of people who says, no, seriously, you should just trust us? And we start with that problem, and we point out that science in many ways actually has brought the goods, right? Like the decades and centuries since the beginning of the scientific revolution in the 1600s really have had just way fewer babies dying of preventable diseases and all sorts of other really impressive improvements. So what the heck is going on here? And so we start with allowing kids to explore the idea that maybe the most basic thing that they think that they know about the world, which is the shape of the Earth. What if it was wrong? How could you actually get to that? And then what we champion, and then champion throughout by talking about the age of the Earth, about climate change, about all sorts of things, is you, in order to actually know that you know something for sure, you have to be willing to engage with people who disagree with you about it. You have to be willing to hear their best arguments, which are invariably much better than you would have imagined them to be, or at least much more convincing on the surface, much more sort of intriguing than you would have guessed that they would have said. And then you need to take those seriously. You need to think about an answer, then you need to answer that. We actually, like, the very first riddle is, how can you really know something? And the answer is, find frenemies to fight you forever. And it's only through that sort of intersubjective going back and forth with different ideas that you're able to figure out, oh my gosh, you actually can figure out what truth is. The truth is weird.
I love that answer. I mean, I personally found out about climate change when I was in 10th grade many years ago. I think before it was kind of controversial. It was more, I was taking a geology class actually at Cornell at university as a sophomore, and the teacher was talking about, the dangers of living next to the water and how houses, erosion. And then we learned about climate change. And I was totally destroyed by this revelation. I mean, it felt apocalyptic to me. And then I went through college and there was a whole, my environmental studies program was teaching us that we shouldn't use like a fear-based approach to talk about climate change. And that felt really strange to me because it was such a scary issue. And now we've come to a point where I was in a conversation the other day with the leader of this homeschool organization telling me that, there was a professor at Stanford who had a really compelling argument against climate change being detrimental. And I just I didn't even know how to respond at all. And so I just decided not to engage with that conversation. And then, in the homeschooling world, we have kind of an issue where because a lot of homeschoolers are religious, and not all religious people are anti-science, quite the opposite. Religion has been a vehicle for scientific thinking for a long time, especially Islam, the Catholic Church. But a lot of these curricula are focused more on selling than on teaching. And so they present climate change as a two-sided issue, when in fact it's more a spectrum of most scientists. And so I'm rambling a little bit here, but the point I'm trying to get to is that, so there's that two-sided approach, and then there's people who just leave it out altogether. And, I'm just curious to know your thoughts on the topic and how you would help kids think critically about this issue and why it's become such a hot topic. I don't know, Dan or Michael, if you want to tackle that one.
I'll jump in. So, Lisa, yeah, great questions. So I kind of take maybe a transcendent or evasive move on these things. So on the record, as an organization, Quantum Courses has no opinion on even evolution or climate change or a flat earth. Of course, has no opinion as an organization. Off the record, I have lots of opinions, but let's put that aside for now. But you take a course, on evolution, you run the labs, you throw the students are collecting the data, they're on the Beagle with Darwin going to the Galapagos Islands and they're looking at the finches. That's just the first little seed of like this theory of evolution that sort of, grew up after Darwin. Kids collect this data. They'll make their own opinion. It's not my job as an educator or as a leader of this organization to worry about how the opinion lands or what the opinion, what manifests in the child's brain. Here are the data. Now, of course, the data is so powerful. Like if you actually study it, of course, evolution is sort of, a real fact of the history of the Earth. Same with climate change. We have a course on biogeochemical cycling. You look at the data, you're going to come to a conclusion. So that's basically how we approach it. And then there's no concern, like literally we're not trying to control thoughts. We're not dogmatic. We're just a bunch of scientists doing what scientists do, and that's collecting data and seeing how best we can make sense of that data.
Dan, did you want to add anything?
Yeah, sure. So I've never really talked to a flat earth person, but that would be fun. But what does come up for me, because I'm doing molecular and more biological stuff, is there's a lot of misconceptions and things that have maybe been pseudoscience and have bled over, and kids kind of think these things are real. It could be things from anything from like, should you take vitamin C when you're sick, to issues with vaccines and things like that. But the interesting thing is that, I come, as a person who has access to explaining and using these like beautiful and complicated structures that are deposited by the world's scientific apparatus into this thing called the Protein Data Bank. And I can show these just like unbelievably amazing looking things that are just beautiful. I mean, this is the reason that I changed from music to science, because I saw a poster for one of these things as some kind of PhD talk. And I was like, I have to know what that thing is. It's these like, rainbows, complicated structure with twists and turns in it. And what happens is that, any kind of, quick answer that these kids might have heard that is, maybe a misconception or pseudoscience or whatever, like, this is way more interesting to see, like, what is that? Like, that's what the kids want to learn about. Like, that's way more attractive than some of these other things. So I don't really ever have problems, trying to convince kids or no one. I don't think anyone like wants to challenge me, honestly, because there's it's just such a beautiful and just looks so good. It just obviously is real, and there's so much of it that we just don't have a problem with it. So that's really what draws kids in, I think, is actually seeing these things and realizing their explanatory power, because these other things don't really have a lot of, the power is very minimal compared to what I can offer them.
I really admire all of your experiential approaches. I mean, just letting people experience and see things to arrive at their own conclusions, and then also to make it a game. You seem to actually enjoy talking with people who have a different opinion than you, and we'll definitely send you to a flat earth conference. I'm curious about, why science. I mean, of course you can say religion, but what do you think it is about science that triggers people so much and upsets people and kind of makes them close in on and not question beliefs?
Grab that one, if you'd, or at least first, if you'd like. I think it's really interesting to look at the deep story of where this thing that we call modern science comes from. You can make a lot of arguments as to, so it's at this date and everything before it was crap or whatever. One of the places that I like to start is with Anaximander in the, what is that, like about 600 BCE, ancient Greek guy in Turkey, an island off of the coast of Turkey, who is the first person to figure out the water cycle, but also evolution. He sort of presages evolutionary theory. He thinks that all animals used to be fish, including humans. He is the first person to figure out that the world was not flat, and in fact that the world is surrounded by space on all sides. He didn't think it was a ball, but he was the first person to do that. And he's at the very beginning of the sort of the ancient Greek revolution in science and philosophy and mathematics and things like that. And I think that we look at the birth historically of science, and we see that science is this thing that moves beyond what our naive, natural understandings of the world are. Atoms are weird. Nobody would intuit atoms. But atoms, it turns out, are the ways that things are. Energy and mass are really weird. The fact that everything, I don't know, is maybe math kind of deep down. The fact that apples are actually literally, like if you have an apple, I don't have it here, right? And apples are literally a breathing thing that reacts to the light and touches and smells of the world around it. And you can watch that happen, right? None of these things are things that people would guess. So it almost seems like we draw the category line for science, like specifically around here are the things that any ordinary human being would intuit about the universe and say, that's not science. Science is all of the non-intuitive, totally blowing your mind, nonsense-sounding truth. And we shouldn't be surprised then that science is actually very offensive to everybody.
I think that's such a great point. And, and of course, connected to all that is death, right? If you acknowledge life, that an apple has a life, then a life ends, your life ends. And that's really overwhelming
How about when you eat the apple? It's still alive.
Oh, freaky. Okay.
Why did you eat it, though?
I want to go a little bit into just what your programs feel like on a daily basis. The touch, the taste, maybe, I don't know. Just the sights, the sounds, what's a typical day like? But then after that, I'm going to invite each of you to ask a question to the other guys. So think about what you might want to ask. Michael, maybe we can start with you because you have such an interesting lab program. How old is a kid when they first sign up for that labs, and what does it look like, the kits you send?
Yeah, so what we did is we basically bottled a science summer camp experience into a science box. We built a online learning platform. And so homeschoolers and micro-schoolers and out-of-system learners around the country can hit a button and they have a full lab science program that just pops up at their school door or their home. And so the experience is, we ship them a kit of stuff. Here's a whole bunch of stuff that I put in the boxes in the back here. And there's a series of articles which bring them into a period of time in history when, like I said before, scientists didn't know anything, humans didn't know anything. And they say, here's what Lavoisier was doing. Here's what Joseph Priestley's doing. Here was what Galileo was doing. Here's what Michael Faraday was doing. They didn't know the answers. They were just running the experiments. like you're going to do, go run the experiments. And so there's all the equipment in the box that they run the experiments. And so the students are literally sort of the discoverers of all the knowledge and of the canon of science of today. And so for the effect, and this is just microschool founders and owners and parents that are telling us, is the kid feels like they are now the author of all of science rather than this passive, like, oh, here's these science textbooks, or here's Wikipedia, here's this, great YouTuber. No, the kids who take quantum courses are the discoverers, are the owners of all of the science principles that you find in any good textbook.
Amazing. Dan, what's a typical class? I know even you do a lot of live teaching, right? And I think there might be some asynchronous classes, or that's in the works. What might I expect as a 6-year-old showing up to my first biochemistry class?
Right. So 6 would be for a very precocious kid. I don't design it for 6-year-olds. I design it for maybe what I would call like a typical 3rd grader should be able to begin the program. A 3rd, 4th grade, that's kind of the target. But there's a lot of various kids that do it. And I think my average age is like 4th, 5th grade or so when they start. Also, so by the way, I agree with Michael. My original plan for this was to do a history of science approach. So in Yale, I was into little tiny Leeuwenhoek microscope lenses, and I made a telescope lens. Like, I really agree with this historical approach, but for biochemistry, it just really doesn't work because you need too much millions of dollars of equipment. So I just can't do it. So the substitute for that is they use the model. So kind of like what Michael's saying is that, because they have this tactile component, they feel like they are constructing something, and I learn from building the models. Like if I'm looking up a new tox, like I did some toxin recently, and it had a really complicated structure, so I built it. And I was like, wow, I learned so much about how this works from the structure of it. So there's a lot of that kind of learning. I don't have labs yet, but it's a kind of like virtual lab because a lot of it is also involving the molecular modeling software, which is a third-party software where the kids just can explore. They can go inside a protein, like look at a drug interaction. It's like, and they can edit it and change it and colorize it and show all kinds of things on it. So there's like a lot of active learning aspects to it. But as far as like the day-to-day, most students who join my program, they're doing the asynchronous course. So it's around a year or so course where the kids kind of start at floor level. They don't have to know anything. They learn about how to look at atoms, how to build molecules, and basically, protein molecular interactions. We build up to biomolecules where they learn about the structure of proteins and DNA and carbohydrates and things like that. And they kind of can complete it there, or they can join some of these Zoom classes. So since the pandemic ended, I have a harder time creating a lot of video content. So the kids who want to learn more tend to join these live Zoom classes, these advanced Zoom classes. And I'm actually piloting new material every week. So every week I create a new hour of content that's like very, very high level stuff. Like basically now it's like medical school level stuff. So we just completed this neuropharmacology unit that took me like almost a year to make. We're on to basically the structure, the molecular structures and pharmacology of the heart. And it's like amazing for me, like, cause that's what makes me want to, like, I have this ability to, research during the week, create awesome content that I wanted to know about. And then I have an audience to share it with like every week. So that's like the feedback loop that keeps it advancing. So between the asynchronous course and then the optional Zooms, that's what my program kind of consists of. And then we also ran this crazy summer camp a couple of years ago, which is a whole nother story. But that was amazing to bring all these kids together who really only knew each other through Zoom during the pandemic. And then we put them all together in a camp for a week. So that was amazing too. I'd love to do that again.
It's so funny. I did want to go into this question of what science do kids need. Usually I get that question from kind of a fear-based approach, like parents want to make sure all the check boxes are checked, especially in homeschooling where you really don't want to be the one failing your kids. That aside, I was just thinking the other day, like, I wish that I could have taken everything you learn in medical school in elementary school so then I wouldn't have to pay for doctors. Or at least, I do also feel like whenever I go to a doctor, I kind of need to move them along a little bit and ask certain questions. And I feel like I know more about my body in some ways than the doctor. So I think, why aren't we teaching every kid to be their own doctor? It'd be great.
I mean, they're not even trying to put any of this stuff in the school curriculum or really anywhere. So it's having created these things, it's so rewarding for the kids to have some orientation about how these things work. It's very cool. Otherwise it's just magic. It's just all magical stuff. And that's where you get the pseudoscience coming into it because they have no idea what any of it is otherwise.
Yeah. I'd also be curious to know you're really in the classroom every day. I think you're probably no one else is doing classroom teaching right now, I don't think. And
well, I'm still
so
teaching in a school as well. So
you're teaching in a school. It's not just a classroom, but all day long in a classroom. And so, I mean, you are familiar with the next generation science standards. Many people see them as kind of a great change in the science standards of school, but also, in my experience as a substitute teacher, people don't have enough time to learn all of them because maybe you're getting science once a week, even in a place like New York City, which is kind of very into all the academic standards. So that's a challenge. But I would love to know in general kind of what you think about the science standards in school and what they have wrong.
Sure, that's for me.
That's for you, teacher.
Yeah, sure.
Classroom school teacher.
Yeah, I mean, when you just see what kids can do when there's no limits and no one's supervising and telling you that this is not appropriate, like I just don't have anything to really say about it. I don't know. I just don't know. I guess they don't know what kids can do. They don't know what I know, I guess. Otherwise, it means that they're trying to stop it, which I would hope is not. But I just feel like this is the reason I did the program. The reason I started this wasn't actually to make a business or anything. It was to show what can really be done. No one has called me up and wanted to know my secret yet from the government or something. But that's why I did it, to challenge the system and to show what's really possible. And where the kids are just to say they're running circles around what's the normal way is like that is a huge understatement. And I'm sure it's true for the other programs here. But there's this like amazing limitlessness to what is possible. And unfortunately, it does require, I think, to some degree, guidance or someone who really knows like a huge amount of stuff, because it's really hard to train a teacher depending on, they may have a great intention, but, someone with a PhD, I was a professor, and I've dedicated the last 10 years to like learning more stuff and like developing the pedagogy even more to make it work for kids. So this was like it's not just an easy thing to say, oh, let's just do med school for kids, but it was this huge like, endeavor to get to this. So I'm hoping in the future that someone eventually sees what this is, and maybe there's some ability to bring this to more schools, because it has been used in schools and it works nicely in schools too. But there's a lot of limitations. There's the teachers aren't trained to do it. There's no real reason for them to do it. A lot of administrators don't understand why you would do this. So there's a whole another story about, how schools have seen this.
Yeah, and I think probably the reason that all of you have seen such interest from the homeschooling community is because homeschoolers simply have more time to learn science. There's so many subjects crammed into the day in the school that you just don't have a lot of extra time for extra stuff.
Yeah. It's not their fault that they can't do it. They have other things that are required by the government to do. And this is some more freedom.
You bring up such a beautiful point, and I think Brandon touched upon this as well, is how being a teacher gives us this wonderful incentive to learn, and how extraordinary that process can be if we're really in teaching as learners. It's truly awesome.
Manisha,
Okay, Brandon. Yes.
I just wanted to just follow up on Dan's comments on NGSS. Yeah, when I first started teaching science, it was the standards before NGSS. I forget what they're called, but they were literally just a very dry list of content standards. Then in 2013, 14, 15, NGSS came out. And as sort of like an anti-establishment guy, I was chagrined to admit NGSS actually is not that bad. The 8 SEPs, science and engineering practices, are really good. They building arguments from data, modeling information, asking questions, building scientific building experiments. They're fine. It's all good. It's good scientific stuff. The issue, and I think Dan touched on this, is the NGSS book is like 1,000-page. I mean, any teacher in any middle school, elementary school is drowning as is. They can't pick up this manual like, okay, I'm going to assess on these 8 things. They're actually, my one critique is it's almost too finely chopped. So there's a point of diminishing returns. Like if you're assessing these micro things, it just takes too much time. It's too much. And then what it does is it sort of usurps or steals the fun. And any time a teacher has to actually prep an actual experiment, which takes a long time. And that's the actual catch-22 with science. As Brandon and Dan just said, teaching science is actually, in my opinion, the hardest subject to deliver, because it takes expertise, it takes equipment, it takes safety, it takes thought, it takes procedures. So it can't be bogged down by these other outside sort of external factors. So yeah, so I have a sort of, you could see I have like this mixed love-hate relationship with NGSS. They get
Absolutely. I
science
mean,
right.
it's the science standards are wonderful, but there's just too many of them really to, and it kind of does, I mean, it makes me think a lot about this question, which I know people are still going to feel is unanswered, which is what science should I be teaching my homeschooler? And there's an approach where you just wait until the kid asks why the sky is blue and you start looking up experiments on Google, or the kid says, I really want to be a doctor. And then you go online and find out that Dan Fried is offering mini medical school, or you just have this insatiable curiosity. Maybe you choose a program like Brandon's that is so focused on, exploring these fun, weird questions together. But I guess, I mean, and some of you are parents too. I mean, how do you think about how much science is enough? Maybe Brandon, you want to, or whoever wants to chime
No, sorry, I just made a weird face.
here. I'm a parent. How much science should my kid be learning right now?
I apologize for the face that I just made.
No.
I mean, the thought that ran through my head was, this is the wrong question. We tried to limit this and find like the minimum amount of science. But of course, I understand that really the question, right, is something like, well, I guess the answer has to start from us asking, like, what is our goal here? I think that as a homeschooling family, one of the things that we do more than everything else is science, and everything is science. When my kids finish their other homeschooling, they get to watch, some science related video on YouTube. We're talking about science at the dinner table. So I think that ideally what you want to work yourself into is a spot where these scientific questions, I mean, I don't know, any kind of question, right? Like, why put a barrier around it for science? But this kind of question asking and puzzling things out together and arguing about things and geeking out, right, to make a family of geeks is just this thing that you're doing all the time. But if you have some sort of, preternatural, inborn despising of all things scientific, then I guess there's probably some sensible answer of what the minimum viable science curriculum looks like. I'm probably not the person to talk about it, though.
I think all of your programs are on a kind of a spectrum of structure versus less structure. I'd be curious, Dan and Michael, how parents can think about what science would be valuable to fit in. And granted, for me, I feel like the question is kind of a mix of science is really amazing and important, and it's not taught enough in traditional school. And please just help me not fail my child. Both of those things are kind of mixed into the question. And starting with the goals is a good place, challenging place too. Yeah, so I don't know what you guys might think.
Yeah, I agree with Brandon. The more, the better. I mean, even like just innately, babies and human babies are scientists. I mean, the first time they, throw some sort of glass or breakable thing off of the table, a toddler, let's say, and it breaks, glass is brittle. That's my test. That's a great scientific experiment. Even the acquisition of language is science. When I see this human say, hello, I love you, that makes me feel good. When I see this human reprimand me, I feel bad. So it's these tests like, oh, that means that it's all this pattern recognition. So science is just innately within us, and you throw, and then that's why I love the hands-on so much. I mean, if you just combust hydrogen and it explodes in a test tube, no kid is like, that's boring. So then it's just not a thing where there's some kids who don't like explosions, or some kids who don't like rockets, or even puzzles. I mean, all sizes of puzzles and pattern recognition. So it's just a matter of that. And so that's on us three, really, is the presentation. And are we scientists and are we educators? Just because like I said before, it is hard to deliver. I mean, not everybody can just create hydrogen and just pop it. People get scared and worried about that, even though it's very safe and very easy to do. But how do we present that? How do we provide that to as many Americans as we can?
Love that. What are your thoughts, Dan?
Yeah, so for me, some of the first pictures that I have of my kid, I actually have a picture of our one kid holding this buckyball right here when he was like a tiny baby. So he's always known what molecules are, what atoms are, and he knows that everything's made of these things. So for him, he'll just bring up, what's the banana smells funny? What's that smell? What's the smell molecule for that? So that's the kind of in enlightenment that this kind of molecular teaching can bring, because they understand that the world is made of molecules, and everything, the properties of everything in their world, like Michael was saying, they come from the molecular underpinnings, basically. So there's a connection between the molecules and what our experiences are. So that's also one of the reasons I think that my program is viewed so nicely, is because it's a paradigm shift for the kids where they're realizing that, the world is made of these things and it's just a little bit of knowledge they need. And then everything's at their fingertips. They can understand how everything works. So for me, like, that's why we have to start this early and not wait until high school when the kids are stressed out and they're just trying to do the math on it to get the, AP Chem grade or whatever, that this is something that kids should be brought up with, realizing that this is part of their world and this is the world.
It's such a gift to be able to think scientifically and for the science that impacts our lives in so many positive ways. I don't want to harp on this too much, but it's kind of still feeling a little unresolved for me. So the homeschooling community, and I hope that this provokes some people listening and that you respond and engage in this conversation, because I'm here with these three incredible scientists, and I'm trying to learn about science. I usually use a critical thinking process, and then I defer to people who I really respect as scientists because of their process. But in the homeschooling community, there are many families who choose not to vaccinate their children. And in New York City, it's no longer, the new administration has created a law so that children don't have to be vaccinated to attend school. And now some people are leaving school because they don't want their children to be around unvaccinated kids. So they're going to there's definitely unvaccinated children at homeschool co-ops, but I guess it's a smaller amount. Anyway, and, there are also many children who have, there's a lot of cognitive diversity in the homeschooling community. And in my time, I have encountered many families who have a very strong opinion that vaccines cause autism, even though personally I have not encountered any peer-reviewed scholarly studies that support that. And yet this is coming from people who are very intelligent and convinced of the research that they've seen. You can respond to this observation in any way you want, but I think that my question is really, as an educator who's engaging with families, what is the best way how would you approach this, in your community?
I think we have to defer to Dan on this. Great.
He's going to defer to Brandon.
Well, he said Dan.
No, I got it.
Why Dan?
I have to do it.
And it bounce it back to you and then back to me.
He's the biochemist.
Yeah, I mean, these things do have a way of working themselves out. I mean, in other countries, I've been reading about, that there's a fear, it's not just the United States where there's a fear of doing, giving a procedure to your child and that you don't really understand. But the thing is, like, it will work out and you will see the result of, like, large amounts of non-vaccinated people. And then they will learn what the result of that is. And then there'll be a shift back in the other direction, probably. So, you can't stop them from the believing. I get the apprehension to not want, because, I mean, this is this whole problem is that they don't understand. Like, I can show them what an antibody looks like and how it works. And it's actually a beautiful thing that it does. But this is a black box for everybody. So, of course, they're going to have a skepticism about it. And that's the problem. That's whatever system of learning that they were exposed to. Like, it did not go far enough to show them modern science. So that's kind of like one of the other starting points for why I'm doing what I'm doing, is because we have this modern world where people are alienated from what makes it work. So, of course, this is what you would expect as a result. When you don't teach people what these things are, and then when they grow up and they have to make decisions about it, they don't know what it is. They've never heard of it before. So that totally makes sense that they do that.
Can I piggyback on that? I think that how I'd engage that conversation would be different depending on whom I was talking to. If I were talking to somebody who was on the vaccine skeptical side, I feel like, I don't know there's anything that realistically I'm going to be able to do to move them particularly to doing it. So maybe not even particularly trying to do that, but trying to engage them in a good conversation with that to kind of, if I'm not the person to slam dunk and change their mind about something, maybe I'm one of the people in that chain. But, trying to get them to explain to me, why do they think that, the rates of diphtheria and the rates of smallpox and the rates of polio went down in these successive waves exactly the moment after everybody in a certain population got immunized for it.
History.
I mean, they'll say it's more hand washing. Oh, why is hand washing is a general thing that the world, this is like one disease at a time when you get the jab. And of course, not all people who are vaccine hesitant or skeptical think that they don't do anything. They just think that the negative effects, and right, like there's a healthy conversation to be had as like what the negative effects are of this, right? The federal government has long had a fund for, I don't know exactly how to say this, but giving money to people who have negative effects from vaccines, right? It's a medical intervention, right? I feel like on the pro-vaccine side, sometimes we want to diminish all of the potential negatives to zero because our side is right. And our side is directionally right about this. But we have to kind of glue ourselves to reality and recognize that this is a somewhat complicated thing. Toward the side who is, my side of the pro-vaccine side, I would say, first of all, have empathy for the evolved creatures that you are talking to. The first thing that you have to do in evolution is have an inside and an outside. And organisms that don't keep the outside out stop being organisms most of the time. I have not a pathological fear of needles, but I would say healthy, moderate fear of needles. And even beyond the pain. And it's important to recognize that. And it's important to recognize that as we move to being able to do vaccines through patches, with these little microneedles or whatever, and we get to remove the vaccine from the fear of actually having something, inserted into your body, we're going to see amazing things there. But then I'd also say that, run the numbers. Say that you have, you enter a homeschool community that is unvaccinated in like the following ways. Have ChatGPT help you think through what is the actual risk that my child and my family is taking on. It sure ain't zero. But it's also not that you're definitely going to die. Getting, using the tools of rationality to really get clear as to what the threats are and trying to say, okay, what is that equivalent to? Is that equivalent to me not wearing my seatbelt, like 3 times a year? Yeah. Okay. Is it not wearing a seatbelt every day? Is that what the odds are? I wear my seatbelt and everybody should wear their seatbelts. But it just helps to get realistic about this in a way that, our evolved human psychologies tend to just sort of fly away from. Science can actually help ground us in what we should be afraid of and how afraid we should be.
I love that. And it kind of makes me think about how it's important to remember that there are facts that we've learned, there are theories, there are big questions, and there are mysteries. And it doesn't have to be either or. You're either scientific or you're not scientific. We had a really good friend, Megan Murphy, who passed away in her early days from cancer. And she was very interested in holistic medicine, very anti-Western medicine. And then as she, near the end of her life, she wrote this beautiful post about how she had come to a place where she was integrating both of those perspectives into her medical care. And I felt that was really powerful. And one of the things I like about all of your programs is that you do bring the sacred and the mysterious into the study of science. Okay, I promised you that I would not dominate this entire interview. Have you thought about some questions that you want to ask each other?
I have a question for Michael, I guess. I was wondering what you do with Lavoisier's stuff. What do you do with this early chemistry? How do you engage in that? How do you make hydrogen?
Antoine, great question. So Antoine Lavoisier, fascinating character, a French aristocrat, all kinds of awards by King Louis XVIII for lighting. He developed lamps for Paris, so he lit up Paris at night. Big inheritance from his ancestors. So he's this wealthy guy. So I'll get to the science in a second, but I can't omit this part. French Revolution hits, and guess what? His head rolls in the guillotine in the 1780s. Unfortunate ending, but he is the one in the history of chemistry where if a 9th grader reads a chemistry book written before Lavoisier, any one of us, we wouldn't understand it. If you read a chemistry book written by Lavoisier afterwards, all of us, even a 9th grade chemistry student, would understand it. So all the syntax, all the symbols, all the sort of the language of chemistry was Lavoisier. So he's sort of the founder of modern chemistry. The one big thing he did was actually two big things. Conservation of mass. So that was suspected, but he's proved as much as you can prove it. So that's a big thing. So chemists always had a sort of a inferiority complex relative to physicists, especially with Galileo and Newton, such titans. This is 100 years later. Lavoisier is 100 years later after Newton and Galileo, a little bit over. chemists, maybe to this day, still have this inferiority complex. But the conservation of mass finally gave chemistry a mathematical foundation that they had been searching for. Mass before equals mass afterwards. You have an equation. So it was this great mathematical foundation that he gave to chemistry. The other thing was he overturned this awesome theory of fire called phlogiston, which was the reigning theory of what fire is for 100 years. He's like, no, that makes no sense. And actually the kids who take quantum courses, by the way, the first experiment they do, it's about phlogiston. We back it up. We actually say in the articles, like phlogiston is the theory of fire. So on the first few days of a quantum course, if a kid walks into their mom and says, hey, I know what fire is, it's phlogiston being released from burnable materials. I tell the mom, say, that's great. Have them believe that. Then 100 years later, a few weeks later in quantum courses, the kid does Lavoisier's experiments and realizes, tracking me, that if you burn something like steel wool or any metal, it doesn't lose mass. So how could it be losing phlogiston if it's losing mass? It gains mass. Lavoisier is like, guess what? There's nothing being lost when you burn something. Something's being gained. You're pulling in oxygen, as you can know, from the air, and that's such a violent, energetic reaction. It produces heat and flames and light. So yeah, that's Lavoisier, oxidation theory of fire, combustion theory, and the conservation of mass. That's his. So yeah, awesome question. Awesome.
It's really cool. Really nice.
Yeah.
I've got a question for the both of you. Right now, my bigger project is to create a approach to all of K through homeschooling that is more intellectually vivid than anybody's been able to do thus far, from classical or from free-range unschooling, by bringing these things together under the sort of vision of this recently deceased educational theorist named Kieran Egan, whose work is sort of the guiding principle of science. It's weird. Sorry, blah, blah, blah. This brings me to the situation where I'm writing a book about how to do this in the early years. And I'm interested to hear from the both of you, what would you recommend parents help their kids do when they're younger than they could be in your classes? And what do you see parents doing, try to do something for science in those young years that you think is actually unhelpful or even anti?
Good, Dan.
For like very young kids, like preschool or something like that.
Yeah.
I just think experiences. I mean, one thing that has happened since I was a professor and now I'm teaching high school is that, they're really affected by the digital stuff. And I would just say more real life experiences, going outside, like looking at bugs and, into a stream, seeing what's going on. So I think that's where science started with for me. As a kid, like I had field guides and I would go outside and try to identify bugs. And the first book I ever read, because I had some kind of reading problem, I could read field guides because it was like this much reading, and I could always I could look at the pictures. So like that's one of the things I would say is just like experiencing nature and like doing things that are not stuck on a screen, because that's always going to. And unfortunately, like I have my program is on a screen also, but I do try to have the physical component, and mine's for a little bit older kids. But yeah, that's what I would say is just have them have experiences, because kids are lacking in what would have been basic experiences for like another generation.
I love that. I'll just basically echo the same thing. Yeah. A lot of these famous, iconic scientists from history actually started out as geologists out in the field, picking up rocks, comparing rocks. So yeah, there's something innately natural and wonderful about a kid just out. I love it, out in the stream. It's fine even for smaller kids to build in systematic exercises and stay away from lots of worksheets though.
Yeah, our 2-year-old sits in the bird feeder. Like I'm surprised she wants to know the birds. Like she's like, oh, that's a nuthatch. Like she like it's amazing. She's like has an immediate connection with the outside. So I think that's really important.
Yeah, naming and categorizing is very a natural thing to do.
I'm curious how each of you respond to the question why. There's a period in a child's development, I think around age 8 or so, or 7, where everything, why? And, some people will answer, some people will get frustrated, some people will say, this, other people will say, what do you think? How do each of you dance with that magical question?
I answer it. I answer it, and then, you engage in the conversation, or I lie to them. I think I don't answer it as oftentimes as I lie to my kids about it. This is actually something that I find very useful in science teaching in general. I actually tell the kids that I lie once every single lesson. That's a lie. I don't always, because sometimes I forget to, and also sometimes I'm lazy. But some kids hate that. If anyone is listening to this and you're like, oh my gosh, sign my kid down, please. That might be a sensible thing to do. Lots of kids really love it because it keeps them on their toes and it makes them realize that, oh, for the rest of my life, I'm going to need to try to sort fact from fiction, and I should keep a healthy skepticism of things. But then when I'm talking to a kid one-on-one, sometimes to just say the most ridiculous answer that's totally false, and then, kind of challenge them to say like, oh, you think that's true? And which also is nice because then you can say things that are even more ridiculous and even more nonsensical, and like the sort of thing, that would come from the ravings of an insane person, but are totally correct. And they won't believe you at first. And then you have to do some work to convince them that, no, this is actually what reality looks like. So, which is nice because it then keeps kind of the drama in scientific reasoning. It's not just about filling facts. It's about making kids crave this sort of knowledge because they get the sense of these revelations and that the world is a much weirder place than it seems to be on the surface.
And ultimately, there's, you can go past Brandon, past Dan in biochemistry and molecules, and ultimately, we have no answer to why, all these philosophical, why we're here, where what was before the Big Bang, even the origin of life on Earth. And so it's okay so I like just allowing kids to be in that discomfort, and that ultimately there's some faith. I mean, science is actually a faith that there is some sort of order to this universe. And so at some level, that you have to just sit with that. And then when we have a chance, I have a question for Brandon.
Go for it.
Okay. So Brandon, I struggle with the electron and the photon in terms of like metaphors, because I don't even know if they exist. Teach me, my friend.
So I will say that I have 2 copies of Feynman's QED behind me right now. And QED is like one of those things that I keep trying to understand the relationship between photons. Oh, I'm sorry, but you're not asking about the relationship between photons and electrons.
It's 2 separate questions. How do you discuss the electron? How do you discuss and represent the photon? You can take one of those.
Okay, I'm going to go to photons because we've talked about that more recently. I'll say for electrons, we start with this really ridiculous metaphor of we shrink kids down to pico world. So they're just a 1 picometer tall. We do this with milliworld and micro world and nano world also.
Just for listeners, that's a trillionth of a meter, right? Okay.
Yes. Thank you very much.
Yes.
Like we were animals for a lot longer than we have been human animals, and we have a lot of cognition that is just designed to make sense of the world around us through our bodies. And gosh, like if you just think about if I shrunk down or if I swelled up, like what would these things physically be like? And that is just this shortcut, this golden road to a lot of understanding. But so we shrink down to pico world and we stand on a soccer pitch. And we notice that in the middle, there is a raspberry. The raspberry is the nucleus. Each of the little drupelets on there is a proton or a neutron. They're different colors. It's weird. And then you hear this weird buzzing that is coming around from all sides. If you look up and you see just these kind of streaks of blue that are going through at these kind of random, but, there's like a pattern that you can kind of see sort of emerging there in the sky. And not just in a circle, a sphere around you, right? But like some of them are in circles, but some of them like are coming close and zipping around you. They're obviously desiring these little zippy things, these fruit flies, we think of them as. They're desiring that raspberry. Fruit flies love fruit, the raspberry, but they always kind of just zip right past it. That's like in the first month what we teach about electrons. We haven't gone deeper into electrons, but then for photons, which kind of presages it, we start just literally with the question of like, what is the shape of light? And we talk about how Empedocles had his, like, it's a line that comes out of your eye, and how Democritus had these tiny little balls that bop around. And Aristotle thought that there's no such thing as light. Light is just the word that we have for when we apprehend something at a distance. And I had the kids argue about all of this. And then we kind of lay out some of the basic discussions. Thomas Young's double slit experiment in 1801, or I think it was 1801. Yeah. And where he found that, okay, like you can make this interference pattern, this wave pattern, so light therefore must be a wave. That came after Newton, where light must be a particle, and we had the kids debate like that whole big fight. I'm getting some of that wrong because Newton was Huygens, I think, Christian Huygens that he was fighting against. And
No, you're right. Newton was particle guy.
Yeah, but when in his lifetime he was fighting against Christian Huygens.
That's
And
true.
then it was after both of their deaths that Young swooped in and proved that it was a thing.
Okay.
And then we talk about the modern double slit experiments and how, my goodness, right? Like the one thing that we know about light is that when it moves, it gets places that only make sense if it is a wave. We talk about that we haven't kind of acted out. And the other only thing that we know about light is that when it lands, it always lands with its full force in one infinitesimally tiny point. And then, like, how do you make sense? Where did the rest of the wave go? How did it know where to go? And we give the major theories of that, the Broy's particle wave theory, which we call ghost waves, and the multiple world, the many world hypothesis of Hugh Everett's, and the what's the one, the quantum decoherence one of it's all your mind, right? The kind of the woo-woo one. And then Bohr's just shut up and flipping calculate, nerds. We're not metaphysicians. We don't ask what's really going on. We just
Yeah.
and ask the kids to argue for each of these or whatever they want to, and then we say in the end, no one has any idea. This is like one of the greatest mysteries in all philosophy or science. That's how we do it.
Awesome.
Well, we have just a couple more minutes. Dan, did you get in everything you wanted to ask?
Sure, why not?
You are anything else? Big provocative question.
Big provocative question.
Good.
I
No
think-
pressure.
Yeah, well, we can move on. It's okay. I don't know if I have any more. provocative-
Manisha, I have one for you.
Okay.
Gosh,
What
okay.
was good about your science education?
Well, I think the best thing about my science education, honestly, is having a mother who really fosters a spirit of critical thinking in me. I don't think that I didn't have great experiences in science, especially chemistry. Biology was okay, but it was mostly memorization, and I was okay at that, the way it was taught. But I will say, just as a Montessori student, I had the opportunity to actually do research projects every semester. So I could pick a topic of my own and go in depth with that. And I think the only other really positive science experience I had was physics and calculus in the way that they were mixed together, and just having my mind really blown about the mysteries of the universe. And, it's funny because Modulo, we really do try to promote secular resources. But for me, science has always been a very spiritual experience and brought me closer to the divine and the mysterious. So I would say I feel very fortunate in my ability to think critically and to check sources and to surpass my own emotional responses by really digging deep into my untested assumptions. But the bad stuff was just really like the rote closed-end lab and just not understanding anything about chemistry, and a lot of shame around that. So yeah, but thank you for asking. I mean, I think, the reason I asked about the why question is because I think my approach to that why question is I see it really as the beginning of a process. And so I often meet that question more with silence or giving the child the opportunity to find the tools to answer the question than trying to answer the question myself. We'll often go to Google together or explore tools that they can use to answer the question. And then sometimes I think that question is actually a request for love and a request for entering into relationship with a child. So it's a delicate balance of trying to understand that. And learning and love are very intertwined, of course. So amazing. Okay, well, I know that some of you have to get back to teaching in the classroom, and I just really appreciate your time. This has been such a wonderful conversation. I really appreciate the work all of you are doing so much, and I hope more people will discover and take these classes. The websites are very easy to find. Biochemistry Literacy for Kids is simply biochemistryliteracyforkids.com. Quantum Courses is quantumcamp.com, and Science is Weird is scienceisweird.com. So you should have no trouble finding these people, enrolling in their courses. I might end up taking some of them myself because I feel like I have some gaps in my knowledge, but really just thank you all so much for being here, being part of the community, and the amazing work you're doing for children in the world.
Thank you, Manisha. This has been super enjoyable. Brandon, Dan,
Thank you
great
so
to meet you
much.
guys.
Yeah.
You
So
guys
thank
as
you so
well.
much.